Alright, this is a video for the hand calculation, and so I'm going to show you how to get these measurements from our model. And the equation is pretty simple, so you should be able to calculate this by yourself. So we need the L, which is the length of the imaginary beam, then the moment of inertia, the I, and probably we need to get the E from nx, which is approximately 30 times e to the 6. So let's open the model. I think you should be able to measure this from the sim, so probably you just need the sim. And I guess the idea is, let me turn off the other stuff. Okay, the idea is considering to consider this. Maybe it's easier to say like this. To consider this piece is a half of a beam, or simply supported beam. So this is a half, and you're gonna reflect this half to the other side. So from this end to the middle to the center of the body, that will be a half of the L, which is here a half of the L and a half of the L. So we have 3 measurements. I guess we can use this one between the curve length to and the projected length. So we can try to find first. Let's find the projected length. So we're going to use the measure distance tool, and first we're going to use projected distance to find the projected distance. Okay, and so since we pick the master copy, so we can project the distance on y-axis. The start point would be the first node on the flat surface. So that'll be this one. If you look from the top, the center, okay, and the end point, we still need a spider. So it would be the center of the spider. So that's 3.6125, which is the same as this one. That's how we got this number. So that's the minimum half of L you can get. So I have the mascot here. That's the approximate cross section. I took a screenshot from NX. So we can say, alright, a half of the which L? The minimum M. The minimum L is 3.6125 inch. Okay, and you can add units here, but let's see. Sometimes units is kind of gets in the way. So name is maybe need to put that 2 in here. So 2 times this. That's the minimum L, and the longest, the maximum L we could get is the curve length. So we need to turn on the polygon. Okay, so to see it clearly, we can turn off the body. That's the polygon, and turn on this. We need to measure the length. So this time we're going to measure the length, and we can pick this edge. Okay, and you don't have to hold down anything, just keep clicking on the edge. and I think I'm clicking on something else. So now I'm gonna deselect that edge. Maybe wireframe, so don't need that. This one. So that's the curve length without those two holes. So we should have L maximum is what's that in 3.4012, 3.4012, and plus the diameter of this hole, which you can get from diameter, and pick this 0.25, so plus 0.25, and plus the radius of this hole. Let's find the radius of this is also 0.25, so 0.25, and this whole thing is a half of the L maximum. So I'm gonna add this times 2, an inch. Okay, we can probably say equal to something. What's the possible? So we got the smallest possible length for this simply supported beam, and also the maximum possible length. So I guess in the class he kind of picked a length in the middle. That's 3.44, and between this and that, if you like to, you can get an average. So maybe we can do something different from him. We can say minimum plus maximum divided by 2, and now 1 inch. So let's use some different number on purpose. Okay. So now we have the length of this cantilever beam. Sorry, not cantilever, simply supported beam. Then we need to find the I for this beam, which is kind of difficult. That's the tricky part for this measurements. So first, the width. Okay, so the width would be I think approximately here. If you like to, you can just measure from the mesh. So distance, this will be projected on the X here to try to make it vertical. Not sure how vertical this would be though. So just eyeball this, and I guess, oh, okay, there's a better way to do this. Yeah, first point, I think we did around here actually, between those two triangles. So this first point and the second point, we can try the one behind, 1.09933, so which is diameter 4, dimension 4. So we can say DIM 4 equals 1.9933 inch. Okay, so we're getting some number that's a little bit off from what he has, but if you're going to do this by yourself, not just copying his steps, you would get different numbers, which is fun, better than just copy. Okay, then okay, the height. Now the height is a little bit tricky. You don't want something on the y-axis. You actually want the height like this angle. So it's going to be just the distance, and let's try. I would say it's a little bit hard. Okay, let's try distance from this point to the top point. And the problem is, if you look from the top, it's actually not that vertical. Okay, and which one is the top point? The first one is the top point. We can move X out a little bit, or we can go to the second point, open this dialog box, and you see this is X direction. We can copy the X here, go back to the first point, which is on the top, and paste the X here. So they're on YZ plane. They're aligned on the YZ plane. And then look from this side, it's pretty much the height of this dimension 3. So I got my dimension 3 is 0.4. I'll just copy this. Showing information window, that's the distance. Control C, and dimension 3 equals this inch. Okay, and what we need, dimension 1, we know that's 0.01 to 0.15 inch. And what else? Actually, this is not dimension 3. That's the highest of dimension 3. So we can say dimension 3 maximum. And if you look at this drawing, this is the highest. That's the smallest. So you want to get an average of this. And he got 0.45, we got 0.44, so it's pretty close. And next, that'll be the smallest. So let's see, we can keep the top point, and the good thing about this masked copy is it's symmetric on the YZ plane. So we can change this point to the middle. Let's see. Yeah, we need to change the bottom point to the middle. So we can change X to 0, and OK. F8, it still looks the same from this angle because it's only moving in and out of the viewing angle right now. And for the second point, for the top point, we need to pick one right in the center. So that's the symmetry line. We should pick this one. And F8, it's a little bit off. So we need to go up some points. Maybe this one. Okay. It's kind of annoying. So F8. Maybe even one higher, or so this is kind of too steep, and then we can go back to this point and see how this bottom point, we change that X to 0, so it's in the middle. Then that's the distance of this C shape, the smallest distance of this C channel. Then that'll be this one. So the value I got is 0.29. I just copy this, and then dimension 3 minimum is 0.1 inch, and we can let dimension 3 equals dimension 3 maximum plus dimension 3 minimum divided by 2, and I want to know what that is. So the average is 0.66, and his value is 0.366. His value is 0.365. So that's pretty close here. Then okay, so we have dimension 1, dimension 2 is the same as dimension 1, and dimension 3 and 4. So now we can get the momentum of area of inertial from X. Then we need to go back to the FEM, just borrow a bar connector and define a new section. Then you can get the properties of that cross section from NX. So you don't really have to go into this collector. You can actually go for insert 1D element section. That will bring you directly to the section manager. And we have 2 pins for the model. Then we can create a new pin using the C channel 2. Okay, so that's the picture I just snipped from here. Then our MaskCAD tool. Let's see, bring this up here. Then so dimension 1 is 0.5 inch, which is the thickness, and dimension 2 is also 0.15. Dimension 3 is 0.367. Dimension 4 is 1.9933. Okay, so let's say we can even say OK to create this section. And since we're not in the bar collector, so we will not change the cross section of either of the bar collectors. So now you can click on this information icon. That's the property of your section, channel 2, and we're looking for Z, I think. Yeah, that's IZ, because yeah, that's the Z. So IZ is, or in my equation that's X, but we're doing this on the Z direction, so IZ is copy. Let's copy this. Inch and force. Okay. Okay, I think this number is the IZ is actually the moment of inertia with respect to the centroid. So you don't really need to do any conversion. Okay, that is the one you need. So let's look at the equation. It's 48. So our displacement is, okay, need something else. P over, so 300 pound force times L, or is it L average. Okay. So cubic, and then divide by 48 times E. Okay, then let's find E here. close this, edit. Okay, that was nylon. So maybe just turn to material view. We'll have steel and information, blah blah. And its modulus is not a good value, but that's math cat. So 2.0694 E2 8, and that would be very interesting unit, micronewton divided by millimeter squared kilopascal. Okay, just use this, then E, then we can times IZ. See this, if this is working. Okay, then we can say what's the value of this H. Apparently not as good as this one. Oh, okay. This force is 100 pounds, so not that bad. And I think you can play with, you know, decimal 5. Okay, 1125. So a little bit further away than this one. So, but that's the process how you get this maximum deflection. Also, we need to measure the maximum deflection from the model. So let's go to the sim, and I forgot which one we used. Maybe the non-contact, maybe non-contact. Z direction. Okay. Then we can turn off the slab. We don't really need to turn off the other stuff, and we can find the distance. We can identify this here and here, those 2 points. And this is not very accurate. Try to use information window. Then still not very accurate. Export to Excel. Then we got this value here, the Z, which is we can say what is delta from NX is, so 14.952 e to the minus 3. I don't know if we can use that. Apparently not. And minus 3 times 3.47 and times 10 to the minus 3 inch equal how much inch? So seems like my model is, or we measure different solution. So this is the one for let's see, for the non-contact. Then in this contact problem, we can do the same for this point to that point. Export to Excel. think that's the one we need. And so nx contact equals 15.818 minus 4.344 times 10 to the minus 3 inch equals inch. So somehow my model is, or maybe we measure different points. Okay, maybe not this one. But anyway, that's the nx deflection, and this is my hand calculation deflection. And also, this is the whole process how you can measure those dimensions from your model. Then you can calculate the I and of course, and the E from the model. Then those three are the answer. Okay. And if you like to, actually, I'd like to add one more question to ask you to get error percentage. So let's say this maximum needed your hand calculation minus the nx results, then divide by your hand calculation. Okay, we consider hand calculation is accurate, equals percent. So that's actually very good. Okay, so 2% of error. Then this is for the displacement. Then for the stress, that's a lot easier than this. So for the stress, you can find the y direction and hide the stuff. Okay, hide these, and the question mark what stress is on this. Okay. Then also, so that's the stress at this spot. Then you can find the distance from this node to the center of that node, and then times 100 pound from the reaction force. That's your moment. So then you can use my over I to find the stress here. So you just need to measure this one distance, and the I, you know how to do it. We measured for this already, so that's the same procedure. Okay. All right. So that's the real last video for this lab. Okay. Thank you.